Now let's look at induced charges. We are saying a charge can build up on an uncharged object by holding a charged object close to it as shown below. These charges that would appear on an uncharged object, a charged object nearby, are called induced charges. Okay, one thing that we need to always remember here is that with regard to induced charges is that it takes place in conductors. So conductors are those materials that allow the flow of charge, such as metals. So they have to be allowing the charges to flow from one place to another, like literally moving in that object. So what we have here is a charged rod, which is positively charged. It is highly positively charged, and it is brought near to a neutral sphere. This metal sphere is neutral. Why am I saying so? Because I can see that the number of positive charges in it are equal to the number of negative charges. We can count them. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's a neutral metal sphere. So when the positively charged rod is brought near to this metal sphere, what happens is the positive charges here on this charged rod will create a force, a strong force actually, electrical force. It has to be highly charged, right? So what it does, it attracts the electrons. So electrons, at the end, we are going to have more electrons at the top part of this metal sphere as shown here. So we now have more electrons at the top than at the bottom. And the way we do it, we always want to balance. We want to balance the number of positive charges and number of negative charges in an object which is neutral, like this one, because it's just that the electrons have now moved to the top part of this metal sphere. But with regard to this rod, no, there is no problem. They can be as many as possible. They can't, you cannot always have them being equal to the electrons that they attract. We are only strict with regard to this object, which has its charges being induced in it. So as we can see, the electrons have been attracted, but remember, they cannot leave this part, so they just remain here at the top part of the metal sphere. And we have here, this is an insulator. Why do we have an insulator here connecting this to the ground? It's to prevent the flow of charges. To prevent flow of charges between the ground and the metal sphere. So if now we place our finger at this point as shown here, while the charged rod is still in place. It has to be in place to achieve this. So while the charged rod, the positively charged rod is still in place as shown here, and you place your finger here at this lower part of the metal sphere, what is going to happen is, because we had positive charges here, electrons are going to move from the ground through your body to the sphere to neutralize it. So electrons flow in to replace the missing electrons. They flow from the ground through your body, because your body can conduct, right, to the metal sphere to neutralize. So we'll end up having the lower part being neutralized, and after this what we have is, if now we remove this, if this is removed, the positively charged rod is removed, we will have something like this. Okay, let me try to draw it. It is okay. So the charges here, they are going to be evenly distributed, because they exert a force on each other, they repel each other, so they cannot just go and group in a certain point in this sphere or region or section, but they repel. Because they repel, they are going to be evenly distributed. I'm going to try to make them evenly distributed. How should I do it? Like this? I think it's better. Yeah, they are going to be like this. They are evenly distributed. They are evenly distributed because they cannot be close to each other. They are unlike charges. Unlike charges repel. So there is nothing that will be keeping them close together, because the rod that has been pulling them, that has been attracting them, has been removed. So they just redistribute themselves such that they are far from each other as possible. So that is what happens. Okay, that's it about induction. Now let's look at the gold leaf electroscope. Yes, this is our gold leaf electroscope. It is an instrument used for detecting the presence of electric charge. It consists of a metal rod on top, which there is a metal cap plate. The rod is insulated from the case. A thin gold leaf is attached at the bottom of the rod. So this is our cap. This is our metal cap. And this is our insulator. And this is our gold leaf. And here is the earth. This one is for earthing. So let's now see how we use it to detect charge. Let's see how we can detect charge on an object. So here we are bringing a positively charged rod. Where a positively charged rod is brought here on this metal cap, close to this metal, actually not touching, right? Just close. What really happens is, because it is positively charged, it is going to attract the electrons. So electrons are going to move further up. So we end up having more electrons here. We end up having more electrons here. More electrons here. Because now electrons have moved up, what we have at the bottom is we have more positive charges than electrons at the bottom. So because there are now more positive charges, they exert a force on each other. They repel. When they repel, what happens is this leaf rises. As you can see, it rises. It rises. It rises because there is a force of repulsion. So the divergency increases because of repulsion. And notice NB, it's about movement of electrons. So it is always about the movement of electrons. They moved upwards. Let's look at B. In this diagram, a negatively charged rod is brought near the metal cap. So what happens now? This is a negatively charged rod. We cannot say the negatively charged rod attracts positive charges, because even if they were attracted, even if there is a force pulling them, they cannot move. Like we said, in a solid, protons cannot move out of the nucleus. So the only thing that moves is the electrons. So electrons, they're going to be pushed down. They're going to be pushed down. So at the end, we'll have more electrons than protons at the bottom part here. So the leaf will rise once again, just as before. Why is it rising? Because now these negatively charged particles, which are electron negative charges, they repel each other. So the divergency increases because there is a repulsion between the negative charges. They repel each other. So that's what happens. The next thing that we would like to look at is the charging in an electroscope. But before we do that, I would like us to look at a demonstration of this electroscope being used to detect charge. So here we are. Let's see now the rod is being wrapped to create a charge on it. So here is our gold leaf electroscope. See what happens. The divergency increases because of the charge which has been detected on the rod. So that's it.